So in the previous lecture we were discussing about these diode connected MOSFETs, and we saw that these can be used as a load in our common source amplifiers also and common gate amplifiers also. So, and then we also learned how to find out the impedance looking into the drain of these diode connected MOSFETs. So we had seen that the impedance, for example, here. So for example, impedance, this Rx, so this is equal to 1 by Gm1 parallel to R01. Similarly, for a PMOS, this impedance Ry we had seen, and that one can calculate using the small signal circuits to 1 by Gm2 parallel to R02. Now one more important thing you will notice here, that when you tie the gate and drain, okay, so the gate and drain of these two MOSFETs are connected. Okay. So when you tie a gate with drain, then this would ensure that the MOSFET is always in saturation. Okay. And for amplifier applications, we want our MOSFETs to be in saturation. Okay. So we are using it as a load, and the gate and drain shorting will ensure that this is always in saturation. Okay. Because for saturation, if you remember, the condition is that VDS should always be greater than or equal to VGS minus VT. Okay. And here if you see VD, right, so VDS is VD minus VS, right, so VD minus VS, and VS is 0, right, source is connected to ground, so VD minus 0, so this is greater than equal to VGS, right, so VG and VD, so both are tied together. Okay, so this could be written as VDS, so VGS is equal to VDS basically. So here I can write VGS is equal to VDS. Okay. So in this equation I can replace this VGS by VDS. So VD minus 0, okay, minus VT, okay, or VD is greater than equal to VD minus VT. So this is true. Okay. That is, the drain voltage is always greater than the drain voltage minus threshold voltage. That is, this condition is always fulfilled. So that means this MOSFET will always be in saturation because gate and drain are tied together. So similarly for this MOSFET, PMOS, the gate and drain are tied together, so it will always be in saturation. So let us summarize the impedance that we have calculated, okay, in a common source amplifier. So in a common source amplifier, the impedance by looking into the gate, okay, so that can be found from this small signal circuit, which is Vx by Ix, and we said since Ix is 0, so this impedance is infinite. Okay, gate is insulated with silicon dioxide layer, so gate is insulated from drain, source and bulk, so impedance, input impedance looking into the gate is infinite. Similarly, impedance looking into the drain, okay, so that is, we had found that this is equal to R0, okay, provided that gate and source are AC grounded. So gate and source are AC grounded, one can find out the impedance looking into the drain is R0. So we had seen this, just to summarize what we have learned. Then looking into the source, okay, into the source. So the impedance we had found using this small signal circuit, that is Vx by Ix here. So this was 1 by Gm parallel to R0. Okay. Now let us talk about common gate amplifier stage. So we have read common source. Now let us talk about common gate amplifier stage. So in a common gate amplifier, input is applied at the source and output is taken at the drain. Right? So input is applied at this source and output is taken at the drain. Okay. Now an increase in Vn decreases VGS and hence decreases ID. Okay. So an increase in Vin decreases VGS and hence decreases ID. So one can write VGS for this circuit, since VG is equal to VB and VS is Vin. So I can write VGS as VB minus Vin. Okay. And for this MOSFET to be saturated, I'll use another relation, that is VD saturation should be greater than equal to VGS minus VT. Okay. And VDS can be found by looking at the circuit again. So VDS is VD minus VS, that is V out minus V in. Right. So this is source, this is drain. So VDS is VD minus VS, that is V out minus V in. So I'll write V out minus V in is greater than VGS minus VT, and VGS we have found here from this circuit, VB minus V in. So VB minus V in I'll put minus VT. Okay. Now this V in cancels out, so we are left with V out is greater than equal to VB minus VT. Okay. Now this point says that an increase in V in decreases VGS. Right. So in this equation, if V in increases, so obviously VGS will decrease then. Right. So V in increases, then VGS would decrease. Right. So I'll write here, if V in increases, so this implies that VGS decreases. So which can be seen from this equation itself. Okay. Now next point says that voltage drop across RD decreases when V out increases. Okay. So obviously one can write a relationship here looking at the drain side. So one can write VDD minus ID, RD is V out. Okay. So one can write VDD minus ID, RD is V out. Okay. So this ID, RD is drop across this resistor RD. Okay. So when voltage drop across RD decreases, that is when this VD or ID, RD decreases, so obviously V out should increase. Okay. So that is what is mentioned, that when voltage drop across RD, that is VD or ID, RD, so when this decreases, so obviously from this equation V out will increase. Okay. So then V out increases and the small signal gain is positive. In common base amplifier using BJT also we had found gain was positive and was equal to GMRC. So here it is GMRD and it is positive. Okay. Now here also you will notice that gain is limited. Okay, because entire VDD cannot drop across RD, similar to what we had seen in BJT based amplifiers. So across RD this entire VDD cannot drop, otherwise V out will be 0 and then this MOSFET will not remain in saturation. Okay. So how much can be V out? Okay. So V out should always be greater than or equal to VB minus VT. Okay. So V out should always be greater than or equal to VB minus VT. Okay. So this puts a limitation on V out. Okay. Sorry, not V out. This puts a limitation on the gain. Okay. GMRD. Okay. So GMRD cannot be more. I mean, AV is limited by, this gain is limited by the drop across RD. So one cannot think of dropping entire VDD around here. Okay. Because V out has to be much greater than or equal to VB minus VT. So here also the same problem, that is limited gain. So gain is limited, so drop across RD is also limited. Yeah, so since gain is limited, so V out cannot fall below VB minus VTH, right? So V out should always be greater than or equal to VB minus VTH. Now one can find out the input and output impedance of this common gate stage. So for finding out the input and output impedance, one can assume first lambda is 0. Okay, so one can find out the input impedance by considering no channel length modulation first, and then we will include channel length modulation. Okay, so let us say channel length modulation is 0. Okay, so one can draw the small signal circuit, a small signal module circuit of this circuit. Okay, so one can draw a common gate small signal model. So input is applied at the source and output is taken at the drain. Okay, so one can find out the input impedance, okay, by finding out Vx by Ix. Okay, so you would notice here that this V1 will be equal to minus Vx. Okay, so Vx is dropping here, so this is Vx. Okay, so V1 is minus Vx here. So one can write this Ix current, so this is equal to minus GMV1, right? So this Ix is equal to minus GMV1. Okay, and V1 is minus Vx, so Ix is equal to GMVx then. From here Vx by Ix is 1 by Gm, or input impedance is 1 by Gm. Okay. Similarly, one can find out the output impedance. Okay. So small signal circuit for output impedance. So output is collected at the drain, so Vx by Ix we need to find out at the drain. Okay. So one can write again the equation for current Ix. So this Ix would be equal to this GMV1 plus current through this RD. Okay. And current through this RD will be equal to Vx by RD. Right. So Vx drop is here. So Vx by RD is the current through this RD. Okay. So I can write Ix as GMV1 plus Vx by RD. So from here, and also you will notice that V1 is 0. Okay. So because for finding out the output impedance, one has to ground the gate, short the gate to ground and also the source to ground. Okay. So V1 is 0. So Vx by Ix, that is this term is 0 now. So Vx by Ix is equal to RD. Okay. Or output impedance is equal to RD here. Okay. Considering lambda 0. Now we can also think of including the source resistance. Okay. So in the common gate amplifier, source resistance can be included, for example here, and then one can try to find out the gain. Okay. So this part of the circuit, that is input part, the small signal equivalent circuit seen at the input, so that can be drawn here by considering that at this node, looking into this node, the impedance is 1 by GM1. Okay. So that means at X I have 1 by GM1 in parallel with RS. So I can draw this circuit at the input. Okay. And can find Vx at this point. So Vx would be simply by voltage divider rule. Vx would be equal to Vin multiplied by 1 by Gm divided by Rs plus 1 by Gm. Okay. So I can write Vx as 1 by Gm multiplied by Vin divided by Rs plus 1 by Gm. Or so Vx by Vin can be found from here. Okay. So if I multiply and divide this by Gm, so then finding out Vx by Vin, so Vx by Vin would be 1 by 1 plus Gm Rs. Okay. So this Vx by Vin I will need here for finding out the gain. I can say V out by Vin is V out by Vx multiplied by Vx by Vin. So Vx by Vin is found. Now V out by Vx, okay, that is V out here and Vx. Okay. So this can be found. In fact, for a common gate stage with no source resistance, so this is the gain is GMRD. Okay. So gain is GMRD, that is V out by Vx. Okay. That is for common gate amplifier without source resistance. So this is GMRD, gain is, or V out by Vx, we can put GMRD in the gain equation, and Vx by Vin is from here 1 by GMRS plus 1. Okay. So this is my total gain of this circuit. Now one can find out the output impedance of this circuit. Okay. So that is output impedance, let us say Rout1 here. Okay. And then we will say that total output impedance Rout, looking here, is Rout1 parallel to Rd. Okay. So Rout1 can be found. Okay. So let us redraw this circuit and let us find out this Rout1 or Rout simply. Okay. So again we draw the small signal circuit of this common gate stage with Rs. Okay. And apply a small signal voltage and measure Ix to find out Vx by Ix, which is equal to Rout. Okay. Now knowing that in this branch if Ix current is flowing, then through R0 it would be Ix minus GmV1. Okay. And let us say at this point the potential is Vs. So Vs is also equal to Ix times Rs. Okay. So Vs I'll write is Ix times Rs, and V1 is minus Vs. Okay. So V1 is minus Vs. Okay. Now one can write that Vx is equal to drop across this R0 plus drop across Rs. Okay. So Vx is drop across this, which is current through this multiplied by R0. Current through this is Ix minus GmV1, and V1 is minus Vs. So that is Ix plus GmVs. Okay. Or simply let us say Ix minus GmV1 multiplied by R0. Okay, here. Plus IXRS, so that is equal to Vx. Now further, if I replace this V1 by minus Vs, I can write this, and then finally I can find out from here Vx by Ix. So Vx by Ix is this much. Okay. And if I say Gm R0 is much greater than 1, okay, then I can write this relation. Gm R0 is much greater than 1, so we are left with Gm R0 only here and Rs. So Gm R0 Rs plus R0. Okay. So this is the total output impedance, okay, without drain resistance. With drain resistance, we'll simply say that now the drain resistance is in parallel with this impedance. Okay. So total output impedance is this much. including drain resistance. Now this common gate stage can be biased via the voltage divider scheme using R1, R2, okay, and R3 here. Okay. So R1 and R2 will establish a potential at the gate, and R3 will provide a path for the base current through M1 to flow. Sorry, bias current, not base current. Right? Bias current means ID. Okay. Now for this circuit also we can find out V out by V in, that is gain. Okay. So for finding out the gain, we will refer to a similar circuit which was created using BJT. Okay, that is common gate BJT amplifier with this kind of biasing. So I'll take you back to the previous lectures and show you that we had calculated it somewhere. So let us see. Okay. So the gain can be found of this circuit. Now one can also now put a gate resistor, a resistor at the gate side, RG, and find out its impact on gain and input output impedance. Okay. And you will find that the inclusion of this resistance RG, it has no effect on the gain or input output impedance, okay, because the gate is not conducting any current. So IG is 0. Okay, so gate is not conducting any current, so there is no effect of this resistance at the gate on gain or input or output impedance. Now let us consider one example of common gate stage here. Okay. So in this example, on the source side, a diode connected MOSFET is used. Okay. So a diode connected MOSFET is used on the source side. So looking into the drain of this transistor M2, okay, one can write the impedance. So impedance of this node looking into the drain of the diode connected MOSFET M2 would be 1 by GM2, okay, considering lambda is 0. Okay. Otherwise 1 by GM2 parallel to RO2 would have come. Right. Similarly, looking into the source of M1, that is this transistor, so one can write the impedance as 1 by GM1. Okay. So 1 by GM1 looking into the source of M1, and 1 by GM2 looking into the drain of M2. Okay. So one can again draw the small signal equivalent circuit seen at the input, that is on the source side, so which would be this circuit. Okay. Now in this circuit one can find out Vx by Vin again, okay, by using voltage divider. So that is Vx would be equal to 1 by Gm1 parallel to 1 by Gm2 multiplied by Vin. Okay, 1 by Gm1 parallel to 1 by Gm2 multiplied by Vin divided by the parallel combination of these two plus Rs. Okay. So from here one can find out Vx by Vin. Okay. So Vx by Vin, from here Vx by Vin would be equal to 1 by 1 plus Gm1 plus Gm2 times Rs. Okay. So we need Vx by Vin and then V out by Vx also. Okay. Now V out by Vx, that is at this point, okay, without including the source resistance, the gain of common gate configuration is GMRD. that is GM1 times RD, okay, without having source resistance RS. Okay. So the total gain can be written. So this is V out by Vx. So V out by Vx is known, Vx by Vin is also known. So the total gain can be written as GM1 RD, okay, multiplied by this. So this is total gain. Now output impedance can also be found. So for output impedance calculations, let us say that channel length modulation is not 0, okay, for M1. Okay, let us say channel length modulation is not 0, it exists, so we'll include RO1 in M1. Okay. So the total gain again would be, one can write, okay, sorry, not gain, R out. Okay. So the output impedance can be written. In fact, we have already calculated. I'll show you here. That is, this output impedance we have calculated as GM R0 RS plus R0 parallel to RD. Okay. GM R0 RS plus R0. So here also we will utilize the same. That is GM R0 RS plus R0 parallel to RD. Okay, let us check. Is it so same? GM R0 RS, GM R0 RS plus R0 parallel to RD. So we have written here GM R0 RS plus R0 parallel to RD. So this is my total output impedance. Okay. In fact, GM1, RO1, okay, again RO1 comes here. Now we have to include RS over here, right? So RS, that is this part, total this part, which is 1 by GM2 parallel to RS, 1 by GM2 parallel to RS. So this is total RS, this much, right? So if I put it here, that is this one here, so we get this equation. That is, output impedance is GM1 RO1 multiplied by 1 by GM2 parallel to RS plus RO1 parallel to RD. Okay. Now let us, we have seen common source, common gate also we had seen. Now let us talk about common collector, not common collector here, it will be common drain, right? Common drain or source follower, so which is equivalent to saying common collector or emitter follower, right? Common collector or emitter follower in BJT. Okay. So here it is common drain or source follower for MOSFETs. Okay, common drain or source follower. So common drain configuration means input will be applied to gate and output is taken at the source. Okay. Now for this circuit, one can find out the gain. Okay. So small signal gain can be found by drawing the small signal model circuit for this circuit. Okay. So small signal model circuit has RL, okay, GMV1, and let us say lambda is not 0, so R0 or R01, GM1. Okay. Now in this circuit, one can see that, I mean, at this point it is V out, so V in, so this can be written as V1 plus V out. Okay. So I can write V in as V1 plus V out. Okay. And V out can be written as GMV1, okay, GMV1 multiplied by R01 parallel to RL. Okay. For this R0 and RL, they are both in parallel. Okay. So the output voltage Vout can be written as GMV1 R01 parallel to RL. Okay. And V1 is V in minus Vout from here. So one can write down Vout is this much. So from here one can find out Vout by Vin. Okay. So if I try to find out Vout by Vin from here, so I get this Vout by Vin as this much. Okay. And this is always less than 1, this product. Okay. Because this is 1 by Gm is also adding up here. So this is always less than 1. Okay. Now let us consider one example of source follower. So in this example, this is my common drain or source follower M1, okay, and M2 is acting as a current source. Okay. That is, NMOS is used to sink the current from output node to ground. Okay, so M2 acts as a current source. Okay. So one can find out the gain of this amplifier. Okay. Okay. So gain can be found by using this relation. Okay. So this relation can be used here to comment on the gain of this circuit. Okay. So here it was RL, and in this circuit it is M2. Now at this node, looking into the drain of M2, I can write impedance offered by M2 is RO2. Okay. So that is, for the previous circuit, if I consider, M2 is acting as RL. So M2 is acting as RL. So I'll simply replace RO2, sorry, RL by RO2 in the previous equation. That is this equation. Okay. So instead of RL, I'll write RO2. Okay. And I get now the gain of this circuit. Right. So the gain of this circuit is this much. Okay. Where I have simply replaced RL by RO2. Now one can also find out the output impedance of the source follower. Okay. So output impedance can be found by inspection simply, or by using the previous equation that we had. We haven't found here output impedance. Okay, anyhow, so that can be found here by inspection itself. Okay, that is, one can write that looking into the source of this M1, the impedance is 1 by GM1 parallel to RO1. Okay, and then you have RL also here. So the total impedance, output impedance, would be equal to this parallel to this. That is 1 by GM1 parallel to RO1 parallel to RL. Okay. And if we don't consider lambda, that is, if lambda is equal to 0, so then one can remove this RO1 from here, and one can write the output impedance is equal to this much, 1 by GM parallel to RL. Okay. So the output impedance of this source follower, so this is very small or low. Okay. And the input impedance is infinite. Okay, that is input impedance looking into the gate. So the input impedance is infinite and output impedance is very low. Okay, at low frequencies only. Okay. So it is useful as a voltage buffer. So we had seen that common collector stage of BJT can be used as a buffer. So we had seen how to use it as a buffer between an amplifier and speaker load, right? So this common drain can also be used as a voltage buffer because input impedance is high and output impedance is very low. Now this source follower can be biased by considering a resistor over here, okay, and also a resistor here. Okay. So since there is no current flowing through the gate, so that means this potential would be equal to VDD. That is, this M1 transistor's gate will be biased to VDD. Okay. And this RS, so this is used to set the drain current. Okay, so the drain current will flow through this RS. So one can write the drain current flowing through RS in saturation. Okay. That is ID is 1 by 2 mu n C ox W by L VGS minus VT whole square. Okay. And VG is equal to VDD. Okay. So I can replace this VG by VDD and VS, that is this point. Okay. So VS is ID times RS. So I can write this as 1 by 2 mu n C ox W by L VGS, that is VD minus VS. So VD minus VS is ID times RS minus VT whole square. So from this I can find out ID, total ID. So we have ID here also and here also. Okay. So this is similar to this equation. Okay. And here we have assumed lambda is 0. Now instead of using RS over here, okay, so one can use a constant current source on the source side. Okay. So if I put a constant current source, then the job of this constant current source is to establish the drain current. Okay. So that is, you do not, this circuit is not dependent on this VDD for biasing this circuit. Okay. So the bias current, that is ID, is established by this constant current source, similar to what we had seen for BJT. So here also. Okay. Now this bias current or current source, so this can be implemented by using a transistor NMOS. Okay. So because NMOS can pick a current from a node and sink to ground, so I can use a NMOS here instead of this constant current source. I can use a NMOS. Okay. And then we understand why these coupling capacitors are present. Okay. So in BJTs, in the previous class, we had seen how to couple a mic at the input of the input base of the common emitter transistor, common emitter configuration of BJT, and similarly we understood how to couple a speaker with the output of the amplifier, right? So we understand why these are used. Okay. Now let us review what we have studied so far. So when we are designing a MOSFET amplifier, we should ensure that MOSFET operates in saturation region, a very important thing. Then second thing is allow the desired level of DC current to flow, that is ID or IC. Okay, so that has to be fixed. Okay, so in fact in biasing we set these two things, ID or IC, or operating point. Okay. Then okay, DC biasing, fine, it is required. And then voltage gain can be calculated by V out by V in. Input resistance is seen between input node and ground, fine. And output resistance is seen between output node and ground. So here the output terminal was floating and here it was grounded. Okay. So this is how we had calculated input output resistances and the gain of our amplifier. Then for DC we had used this model, okay. And for small signal AC we had seen or used this model. Now in a common source we had seen that gain was large but was less than 0. That is, negative gain was seen, so the gain is less than 0 but it is large, and the gain is further degraded by the inclusion of the source resistance. In a common gate we saw a large gain which is positive, and again it is degraded by RS. Source follower, the gain is greater than 0, less than 1. Input impedance in common source was high, okay, large. Common gate it is small, source follower it is large. Okay. Output impedance in common source is equal to RD, okay, without considering the channel length modulation. Okay. Similarly in common gate also it is RD, and in source follower this is small and it decreases further by inclusion of RS. And the inclusion of channel length modulation, that is when we include R0, for common source we had seen gain decreases and R out also decreases. Okay. In common gate we had seen gain decreases and R out decreases, both gain and R out decreases. Here also we had seen both gain and R out decrease when we include the channel length modulation R0. Okay, so in fact these all are the biasing, completely biased stages. Common source stage for example, and we have calculated the gain also, input impedance also, and output impedance also. Similarly for common gate, with this biasing we had calculated gain, input impedance, output impedance. Then for source follower also, this circuit we had calculated gain, input impedance and output impedance, both for lambda 0 and lambda not 0. Okay. So we know how to do all these things. So we have learned in this course so far. Now let us consider some examples of common source stage. Okay. So for example, this circuit. Okay. So in this circuit, this transistor M2 and M3, so they are acting as load. Okay. So that means I have two loads connected in parallel at the output. Okay. That is M1 and M2. Okay. Not M1 and M2, M2 and N3. Okay. So this circuit can be simplified to this. So provided I know how much is the input impedance, not input, how much is the impedance offered at the drain of M2 and at the source of M3. Okay. So at the drain of M2 the impedance offered is RO2, and at the source of M3 the impedance is 1 by GM3 parallel to RO3. Okay. So this is, we have understood how to calculate this. Okay. So that means this resistance is RO2 and this is 1 by GM3 parallel to RO3. Okay. So this is common source with drain resistance. Okay. So the gain can be written for this circuit. Okay. So for common source the gain is minus GM RD parallel to R0. or GM1 RD parallel to R01. So this is the total gain for this circuit. Okay. And RD is this much, that is R02 parallel to 1 by GM3 parallel to R03. So I can write this gain as minus GM1 RD is R02 parallel to 1 by GM3 parallel to R03 and then parallel to R01, right? So the total gain is this much. Similarly, I can find out the output impedance. So for finding out the output impedance, again I'll utilize that the impedance looking into M1 from the drain side. So that is R01. Okay. So the output impedance will have all these resistances or impedances in parallel. That is R01 parallel to R02, parallel to 1 by GM3, parallel to R03. Okay. So that is my total output impedance. Okay. So this circuit was looking complex, but when I know that these are simply loads to this common source stage, so the analysis becomes simple now. Similarly, let us consider this example of common source stage again. Okay. So here this M1, this transistor, this is acting as common source stage. Okay. So M1 is acting as common source stage. Okay. And this M2, which is connected to the source. Okay. And M3, sorry, M2 is here. So M2 is serving as a load. Okay. So I'll draw this circuit once again. So this is a PMOS now. Source is here, drain is here. So and the output is also here, V out. So load is connected to the drain and source has a source degeneration resistance. Okay. So this is my RS, RD, and here is my input. Okay. So the gain of this circuit, common source, so we had seen it was minus GM RD by 1 plus GM RS. We had calculated some time back. Okay. So if I can find out RD and RS here, okay. So RD is simply implemented by this M2. Okay. And the impedance by looking into drain of this M2 is RO2, which is equal to RD here. Okay. So RD is RO2 here, and this M3, so this is acting as this RS or degeneration, source degeneration resistance. Okay. And looking into the drain of this M3, okay, the impedance is 1 by GM3 parallel to RO3. Okay. That is RS is 1 by GM3 parallel to RO3. Okay. So now we have RS also, RD also, everything is known. Simply I have to put these values here in this equation. So when I put these values in this equation, I get gain as this much. Okay. So again, a complex looking circuit can be made easier. Okay. For example, if I know the roles of all these transistors, I can simplify the circuit and then find out the gain. Also, output impedance can be found now. Okay. Now another example here. Okay. So let us see what it is doing. Okay. So this is the common source stage. So in fact, both these two circuits are identical. Okay. I mean, these two are, this is common source amplifier and this is common gate amplifier. Okay. And both of these two circuits are looking exactly same. Okay. The difference you will notice is that input is applied here in common source at the gate, and in common gate the input is applied at the source side. So that means this M2 is acting as common source, common gate. Okay. And here M1 transistor, this is implementing common source. Okay. Common source input is applied at the gate and output is taken at drain. And common gate, that is M2, input is applied at the source and output is taken at the drain. Okay. This is drain, source. Okay. So that means this is common source acting as a common source now, and this is acting as a common gate. Okay. So they were looking similar, but now we identify that this is working as a common source and this is working as a common gate. So for finding out the gain, I'll apply the gain of common source amplifier, which will be negative, that is minus GMRD. Okay, so I'll use minus GMRD. And here for common gate, I'll use this equation, positive gain, that is GMRD. Okay. If I have RS also, so I'll include 1 plus GMRS. Similarly here, if I have RS, I'll include 1 plus GMRS. Okay. So we have RS over here. Now, knowing that, for this circuit, looking into the drain of this M2, so I can write RD. Okay, let us say looking into the drain of this transistor, the total impedance is RO2 plus GM2 RO2 RS plus RS. So this we had found, so we are simply using the output impedance that we have found here. I'll show you. So we have found today this output impedance for common source, that is this one, this part. Okay. GM R0 RS plus R0, right? So this is same. So we'll utilize the same to find out the impedance. So let us go back to that circuit. Here, so looking into the drain of this M2, I can say that the impedance is RO2 plus GM2 R02 RS plus RS, using the same equation that I have just now shown to you. Okay. So this will act as RD, the total RD. Okay. Because I am considering this as a common source amplifier with with drain resistance, that is RD here. So this is common source M1. Okay. So for this, gain is minus GMRD, okay, GM1 RD, and RD is known to me. Okay. So from this I can find out the total gain. Okay. Minus GMRD. In fact, if we are considering lambda, so it should be RO1 also should come here. Okay. So if I put RD here as this much, okay, so I get this gain as this much. Okay. Similarly here, I know that this is a common gate with drain resistance, that is this VB M1 is acting as drain resistance. Okay. And looking into the drain of M1, I can find out the impedance, which is equal to RO1, which is acting as RD. Okay. And the gain of this common gate amplifier is this much, AV GM2 RD by 1 plus GM2 RS, okay, where RD is this much, RO1. Okay. So I can simply put in this equation RD as RO1, that is GM2 times RO1 divided by 1 plus GM2 RS. Okay. So this is my total gain of this circuit, which is exactly equal to this gain. Okay. So this is how I can find out the gain of this stage itself. So I'll stop here, okay, because time is also over, so I'll stop here.